All right, so we can apply the squeeze theorem to help us solve one of the more important theorems, which is the mystery of what is the limit as x approaches 0 of sine x over x. And you know that I told you that the first thing you need to try is plug and chug, but in this case, if I do that, I would get 0 over 0, which is not a thing. So I have a couple steps of what the squeeze theorem would look like if I were trying to solve this particular question. And then I'm going to get to the point where I can't do a whole lot. So I'm going to refer to a graph to show you what's going on. So in Desmos, we have the green line is the reciprocal function 1 over x. That's a parent function from last year. The purple would be the same thing but reflected. And then the blue is what we're trying to find. And so if you look, the blue line is sandwiched right in between of these other two functions. So we can use the squeeze theorem to find that this limit is undefined at that point, but the limit is approaching the value of 1, okay? So that's going to lead us to our next special trig limit, which we're calling limit procedure 4. And this is probably one of the more challenging skills to figure out because it involves a lot of trig and algebra at the same time. So just in general, we're going to take this as a true statement always, okay? So the limit of sine x over x as x approaches 0 will always equal 1. And actually, we could also say, kind of like a second part to this, is that the limit of the reciprocal would also equal 1 because the reciprocal of 1 is 1. You know what I mean? So both of these things will always be true. They're both super useful in solving trig limits. Let me show you why or how. So if I say find the limit of tan x over x, the first thing you're going to do is you're going to try to plug it in, except when you do that, you get tan of 0 over 0, which is incomputable. Okay, so we're going to then try to invoke this new special trig limit. The way that we're going to do that is we are going to kind of split this up and call it tan x over 1 times 1 over x. See what I'm doing? I'm just splitting up the fraction so that there's only one item in each fraction from the original setup. But if I multiplied them back together, it would equal this thing up here. And then I'm going to use what I know about trigonometry, and specifically what I know about tangent. I know that tangent is equal to sine x over cos x. Okay? I know tangent is equal to sine over cos. Then I'm going to take what I've got and I'm going to try to find something that looks like that special thing. I want to try to find something that looks like sine x over x because I know that that is always equal to 1. Okay, that's a solution that I can use to help me get through. Oh my goodness. Wow, I'm a mess, you guys. Okay, let's try again. There we go. So I'm going to switch some things around. So these two denominators, if I were to just switch them, which I can do, because multiplication, you can switch the order of stuff. But if I were to switch them like this, then I would end up having something that has the limit of sine x over x. Okay? Now from here, I'm going to apply my limit properties. And I'm going to say, I'm allowed to split this up and apply the limit to each piece separately based on properties. And then I could say, I know the limit of sine x over x is 1. And then I could find the limit as x approaches 0, actually, of 1 over cos x by doing plug and chug. So 1 over cos of 0, cos of 0 is 1, so this whole thing would just equal 1. Let's try another one of those. Okay, here is an auxiliary rule. So if I have the limit of sine x over x as x approaches 0 equals 1, right? Then the same would be true if x was something more complicated. So this could be sine of 2x over 2x, or 2x squared over 2x squared. Do you see what I mean? The important thing is that this inside piece is the same as this bottom piece. Okay, so I am actually not going to split this one up like I did last time. And the reason I'm not going to is because it almost looks like sine x over x, except this 4 is here. The 4 can stay where it is, and as long as I have a 4 on bottom to match it, then I could use this special trig rule that sine x over x has a limit of 1, okay? So in other words, if I can make this look like sine of 4x over 4x, then I do know that that limit would be 1 as well. How can I make this have a 4 on the bottom? Well, if I multiplied and put a 4 on the bottom, then we'd be good. But algebraically, that doesn't make sense unless you multiply the top by the same thing, right? Got to have everything balanced. So I'm going to rewrite this in a way that looks a little bit nicer for what I want. So what I'm going to do is I'm going to pull this 4 over to the bottom. That way I have sine of 4x over 4x. And I still have this 4 on the top, okay? Then I'm going to do limit properties to take this 4 that's out here and bring it to the front. And I'm going to say I've got sine of 4x over 4x. And this is like a variation of the property that we learned. And we learned that it has a limit of 1. And that 4 on the outside will just multiply by my answer, so I'll get positive 4 for my total limit. Okay. I think I have just a few more things. So in this one, it's going to get very, very messy. So I'm actually going to have you wait until class on Monday, and I will do this one together with you on the board. So that takes us to limit procedure number 5 that involves absolute value and piecewise functions. Okay, so when we have weird looking graphs like piecewise functions, absolute value is a piecewise function, you're going to have to do two things. You're going to have find the right-handed limit and the left-handed limit to see if they match, okay? So when it says find the limit of absolute value of x as x approaches 0 and show that it would be 0, that doesn't mean draw a graph. That means explain algebraically what you know about absolute value. So what we know about absolute value is that it actually contains two equations. Negative x is the equation for any x value that's smaller than 0. And positive x is the equation for any x value larger than 0. So we're going to find the limit of each of these two pieces separately. Okay, we're going to find the limit from both directions. So for negative x, this applies when any x value is smaller than 0. So I would be approaching 0 from the left side because anything smaller than 0 is like the negative side. And over here, the limit for positive x would be approaching from the right side. Okay, so really, once you set it up, you could just kind of do plug and chug from there. So like if I plug in 0, I would just get 0. And on this side, same thing, I would get 0. But the big important concept here is that when you take the limit from the left side and you take the limit from the right side, if they are equal to each other, then your limit from both directions is equal to that value. Okay? So you have to verify the left-handed limit and the right-handed limit and verify that those two things are equal. Okay, so let's do one more actually like that, and then I'll review the summary page. So here's another example. This is a piecewise function, and I want you to tell me the limit as x approaches 4. Well, since it's two different pieces, we're going to have to look at the limit as I'm coming from the left, and we're going to have to look at the limit as I'm coming from the right. Okay? We're going to use two different equations to do that because the equations are different from each side. So from the right side would be anything greater than 4, which is this top equation. So for the right-handed limit, I'm going to use the top equation. And for the left-handed limit, anything smaller than 4, I'm going to use the bottom equation. Okay? From here, I can plug and chug, just like we've been doing. So if I plug and chug here, I'm going to get, let's see, 8 minus 2 times 4, and that would give me 0, right? And on the bottom, I would get square root of 4 minus 4, which would also give me 0. So as we said, if these two limits, the left and the right-hand limit, are equal, then that means that the whole limit, and this function is called f of x, is equal to that same number. Okay, so I made you a little summary page where it tells you the procedure or like the steps to follow to make your life easier when evaluating limits, because it's a lot of information. So the first thing you're going to do is you're going to try to do plug and chug. And I wrote, assuming kittens don't die, that just means that you're not dividing by 0. I don't know if your teachers ever told you that every time you divide by 0, you kill a kitten. That was something a teacher told me when I was younger because it was so important. They didn't want me to forget. So really dark, twisted joke, but it helps you remember. The second step, if plug and chug doesn't work, then you're going to try to factor, cancel, and plug and chug again. If that doesn't work, go to step 3 and try conjugate. If that doesn't work, then you go to step 4 and maybe use a special trig limit if that's what you're dealing with. Or 5 and use the absolute value piecewise function procedure. Or you do have the squeeze theorem, that's an option. Sometimes just depends on the way that the problem looks.